How's it going, everybody? In this video, I wanted to cover something that isn't CLI centric, and it's not me just, you know, basically just talking about just random things. In this video, I wanted to cover something that I find increasingly surprising as I progress through my career in the networking industry. And the problem I have with these scenarios that I run into is there's no redundancy. Okay. Now, when it comes to redundancy, there's many ways you can look at this. There's physical connectivity redundancy. There is dual power supply redundancy, dual supervisor redundancy. Um, all kinds of redundancy can be looked at from power, connectivity, um, management, control plane, back plane, forwarding. There's all different ways you can look at redundancy. So one of the common things I find that people don't know, or there's usually a lack of, is redundancy. And typically it's because of the fact that um, you have a couple of things that come into play when it comes to redundancy immediately out of the gate. And so what I'm going to do here is I want to break down what those are real quick for you. The first one that I'm going to break down for you is going to be the capital expense. Now, you typically won't hear me talk about this when it's a technical video because of the fact that a capital expense versus operational expenses typically fall on the solution architecture, the pre-sales, that type of stuff. So it's before I get into the mix is when this discussion happens. Now, Capex, as it's affectionately referred to, is the upfront. Oh, let me erase that because I can't even spell Capex. Capex is the upfront cost to buy the equipment. So you have Capex. So that's the capital upfront expense to buy the equipment. So the procurement of equipment, stuff like that. Then you have your opex. Now, opex is the day-to-day operational expense that it's going to cost to keep these devices operational. Now, what are some of the things that you need to worry about when it comes to Capex? Well, how much does this device right here cost? How much does this device cost? And it depends on where you go and what your means are to procure the device. So let's say you go to Amazon. You go to Amazon and you punch in, you want to get, and if you're wondering, this is a Catalyst 4506 and this is a 3750. Okay, two very common devices you'll see in most modern networks. So let's say you go to Amazon and you pick up a 4500 Catalyst switch for, let's say, $3,000. Okay, so $3,000, and you pick up a 3750 for, let's say, 1,000. Okay, I don't even know if that's even remotely close. I didn't bother to look. They're just random figures I'm pulling out of the sky. So you buy, in this case, one Catalyst 4500 and one Catalyst 3750. Now, your main goal, and regardless of what your role is in the network or in the company, is to get access to end devices, have a core device that's going to be providing upstream access to whatever it might be. This might be your core router, and it might connect up to a firewall or a modem, and this might be your internet gateway. So typically I see this in smaller environments. You have just one Catalyst 4500, you have one Catalyst 3750. It doesn't even have to be Cisco. This could be an HP, what did I just put in? 5406, I think is what the model number was. And this guy right here was a 2920, and I think a 25 something. And it was all HP. Relatively easy to work on. It was a very similar CLI syntax, and it wasn't very difficult to put in. So this is what I did for a customer. He had an HP core, what I refer to as a chassis-based switch and a modular switch, meaning that you have this guy right here is connected up to is the access layer switch. This is the core, and these guys are just a single fiber uplink to the core switch. So this is what I did for the customer. This was his design. There was like a bunch of different things that came out of me. He had dual power supplies, so that was good. He had two supervisor modules. So I don't know if you can tell, but I'm going to change my color to red real quick. But this guy right here, This is the supervisor module. Down here we have a fiber, and then I believe we have another fiber. I can't tell by the picture, but I think this is a fiber as well. And then we have a bunch of regular Ethernet or Ethernet cabling type setups. I haven't zoomed in to actually look at what the ports are, but this is just a picture I grabbed off of Google. So we have a situation like this. Other than the dual power supplies and a single supervisor, this is a poor design. The reason I say it's a poor design is because of the fact that if anything goes on this box, other than if a power supply fails, you at least can fail over to this guy. If this power supply also fails, guess what? The network is down. Like, network down, hard down. There's a difference between a soft down and a hard down. The difference between the two is a hard down means that a physical box is physically incapable of operating, where no power, no forwarding, where a soft down is typically a software failover, whether it's staple switchover, whether it's a nonstop forwarding, whether it is a you have an uplink goes down and you fail over via like HSRP or some sort of first hop redundancy protocol, things like that, where that's a soft down because of the fact that it's still moving, but software had to kick in to move how you're going to get the job done from one method to another. Now over here, this is what I would consider to be the proper method. Now the proper method is typically more expensive up front and a little bit higher operating cost. But what does this give you? It gives you dual power supplies. And for the sake of argument, dual supervisor modules. So it gives you a lot of flexibility there. The other thing here it gives you is we have two core switches. Okay, then we have, this could be DMZ potentially, and then we have access layer, or this could be, your server blades or what have you. And down here we have our access layer. So these are, again, 3750s and whatnot. So, and then in between here we have a, let's just assume for the sake of argument, we have a virtual switching system. And if you're not familiar with that, VSS is a way for you to take the supervisor modules and have these guys talking to each other across the VSS. The VSL, or the virtual switch link, is going to be the link between the two connections that allows the supervisor modules to sync the layer 3, the layer 2, the routing, all the different control plane mechanisms between the two devices. Now this is just one example of what they refer to as high availability in the campus LAN. So you have that, and then you also have for the 3750s, the 3850s, I think the 3650s had the ability of doing what they call stackwise. Stackwise is where you take the switches and you rack them, and instead of having a chassis here, you have just regular switches that are standalone devices that are able to be what they call stacked together. So there's a cable that physically connects switch 1 to switch 2, and you join, you have one of these switches become the master of the stack. So let's say the switch 1 is the stack master. So this will be the master, this will just be, alright, this is the master, this is a member. The difference between the two is the master is what maintains the control plane. The stacking cable between these two guys provides all the backplane connectivity. So any type of connectivity between these two devices that would normally go over an Ethernet connection or a fiber connection would go over fiber, goes over the stack cable. So you have that in play. So that's just another variation of that. In Nexus, they usually refer to this as VPC, or virtual port channel. There's a lot of different ways of getting the job done depending on the platform you're working on and the method or the design that you're trying to achieve. It really depends. Cisco's got a lot of really good Cisco validated designs, or CVDs. And if you were to Google CVD or the SRND, or Solution Reference Network Design, they have a lot of really good docs on how to build a very highly available network. What I have here over here on the right under the high redundancy is a very highly available network. And there's a couple different things that come into play with this. You have one which is going to be dual power supplies. You have another one which is going to be dual supervisor modules. You have another one which is going to be dual links between the core switches. you have dual uplinks from every device to every other device. Now, these are built in what they refer to as the triangle method. So this is going to be like this. You want to build triangles. So what a triangle allows you to do is when you're building, and this is basically for your spanning tree design, assuming you're going to be running spanning tree. I know a lot of customers lately. I've only been working for the reseller that I've been with for a very short period of time, less than 6 months, and a lot of the customers I've worked with, we have actually gotten rid of spanning tree and moved over to a routing design where it's applicable for them. And we actually go to them and say, okay, we did a quick network assessment, and we think that we could, for a very small nominal fee, which is just a couple hours of my work, we can make your network more redundant, more highly available by enabling a layer 3 routing protocol. And we've identified that which devices are capable of doing that and which devices aren't. And then we offer them a design. And this is one of the things that we do as what they call a value-added reseller. That doesn't just mean when we call value-added, or value-added, sorry, that typically means that we try to save the customer money in some way, or we try to optimize their network in some way, as well as try to save them money in some way. And one of the ways that we try to optimize their networks is to identify potential issues in their network, whether it's during the current deployment or whether it's post-deployment and we're monitoring. So one of my jobs, and one of the things I take pride in what I do, is going to my customers and saying, hey, just so you know, and this is an FYI, not to scare you, just to let you know so you have a realistic understanding of what's going on in your environment. This is what your devices are doing. And a lot of this stuff comes from, we do what they refer to as an as-built post-deployment. What that means to you is, and well, to any customer that I work with, is that we take the connectivity. So this would look like an as-built, except for I would do it in a Visio, and I would say, okay, I would identify what this connection is here, this connection is here, and I would identify, okay, this side would be connecting to the 4500, what port number it's connecting to, and then I would have another one for, that's the physical connectivity, and then I would have another document, same physical breakdown, except I would lay out, okay, you've got, this is a trunk link, it's allowing these VLANs, so on and so forth, and then I would do a third one for the routing. Okay, this is where your routing domains sit. And by providing that level of documentation, if whether that customer decides to stay with us or go to another reseller or to support themselves, they've got very detailed documentation that I took the time to put together and delivered to the customer that says, okay, you have this going on here, this is what it's doing, and if you run into a problem, instead of trying to sort through the CLI or a GUI management application to try to figure it out, I'm telling you in a Visio what's happening. I know not everybody does that, and it's more of we do this pre-assessment and post-assessment to see exactly how everything's working. We had deliverables we have to do. So all of that kind of ties back into what I'm doing here. So for instance, with the spanning tree, and there's a reason why I went into that detail, so I could kind of wrap it back up in the spanning tree. Typically, when you're building network designs like this, you're building them in triangles. So I'll draw out one of the triangles. One of the triangles is right here. And you have a connection here. Squares typically there will be a blocking link somewhere. Now, there will be a blocking link somewhere here in the spanning tree, but by using triangles and not squares, you're able to better utilize the capability. Now, what I mean by that, if we were to build a square, that means that there would be a connection from this switch to this switch down here. Now, I don't want an access layer switch using another access layer switch to get off the network. That is not how I want it to do. So even if this was, let's say this is a 10 gigabit, this is a 10 gigabit, and this is a 1 gigabit. If something happened in the network and this link went down and this link went down, yes, I would have a third layer of redundancy. But let's assume for just a moment that the individual putting this network together doesn't know anything about the spanning tree protocol. If you don't realize that this guy has the oldest MAC address, then what would end up happening here is this guy would become the root bridge for your spanning tree domain. So you're going to send your traffic this way, right? So the problem with that being is if this is the root bridge, something catastrophic happens, then you're going to have a problem. So forwarding mechanism wise, you would still forward upstream, but that depends. Would you be forwarding up here? Let's say that this port right here is blocking. This guy's forwarding, and this guy's forwarding. But let's say, for instance, this guy's blocking. Well, now you have no choice but to go this direction. But you don't want to do that. By removing this link from here altogether, you remove that capability. So you keep the triangle method, which is the ideal method. Because then if anything happens here, let's say this is the upstream method, you would make this the root bridge, the primary, and you would make this the root bridge, the secondary. So what you would do here is typically you make the root bridge, whatever your default gateway is, you make that the root bridge for that particular VLAN. So the way you would do that is you would configure your SPIs, and this is assuming you're using a Catalyst, well, any layer 3 switch that's got the capability of doing layer 3 switching. If that's going to be your default gateway, you make that the root bridge of your network for that those VLANs. And then if, let's say for instance, you're using HSRP between these guys, you then go in there and you configure this guy as your secondary. And with HSRP, you would have, let's say, you know, the 10.1.1.0/24 network is, you know, whatever VLAN. Let's say VLAN 1, even though I recommend nobody use VLAN 1, still people use VLAN 1. What you would do then is you would go in and you would say, okay, this guy here is going to be .2, this guy's going to be here .3, and HSRP with a standby address is going to be, for the virtual IP, is going to be .1. So that means that as long as these two guys are up, if something happens with maybe this link gets cut, HSRP is automatically going to fail you over to this switch over here, and the IP, the default gateway and the virtual MAC address is not going to change because of the fact that they're both sharing the same IP, they're both advertising the same MAC address. And there's a common question too, if I do something like this, is it actually going to forward like that? Well, no, it wouldn't. And the reason why it wouldn't is because of the fact that if you're using VSS, you wouldn't need HSRP because of the fact that this would be the same device. So instead of it looking like this, it would actually look like this, respectively. And the reason for that is because the VSS would make these two guys look like they're the same box. If you don't have the ability to run VSS, or for whatever reason, and you decided to go with the HSRP or maybe a VRRP or a GLBP design, then you would be able to go in here and you would be able to create the .1, and then it would look like this design right here physically. But with VSS, you take both switches, you make them look like one, and then you go in here and you connect this uplink here to there and this uplink to there, and then it looks like this design over here, because the fact that the upstream switch looks like the same, and the same thing down here. So if anything happens, and you would port channel these guys together, so this would actually become a big port channel between here and between here and here. And this way here, you'd be bundling your uplinks. So there would literally be no issues in failover unless, you know, both links got cut or the power went out to both devices, something like that. So it really depends on what your network design is trying to look like. I typically walk in and I try to have every network that I ever work on, regardless of the size or the complexity, I try to make them all look like this guy over here, the high redundancy. The reason for that is because I don't get a phone call in the middle of the night because of the fact that there was an issue. Makes my job that much simpler. Now, I did recently have an issue where I got called. It was, I think, 3:30 in the morning. My phone rings, and I wasn't on call at all. But because I'm a senior level engineer, I am on the always on call list for extremely complicated or highest escalation possible. Typically, in the company I work for, that means that the first on call guy and then the backup on call guy neither of those guys are able to fix the problem, and so they resort to me. There's a lot of senior engineers that I work with that basically what we do is, I'm senior network, there's other guys senior systems, and we have other guys that do security and software, but they're not really considered senior engineers because they're not doing customer projects. So they're, you know, not customer facing. I'm customer facing a lot. Now I'm also internally facing. So what ended up happening was and I don't like to use the term junior engineer, but like, we'll say just a regular systems engineer was on call. He called uh, the secondary guy, the backup, in case the first guy was unavailable for whatever reason. He called the secondary guy, who was technically senior to him in the hierarchy of the company. He went ahead and he looked at it for a few minutes and said, "You know what? I'm not sure. Let's call Rob." And so 3:30 in the morning, my phone rings. The customer was actually a hospital, and the hospital had a core switch go down. So they had two core switches just like this, but they weren't HSRP, they weren't BSS. I had never actually worked on the customer. I had no idea what their environment looked like. The customer had already been in play, had been set up and stuff like that. I had absolutely no, I had not touched the customer at all. So for me, when I walked into or when I got the call and I started digging into things, I started noticing, okay, well, why is this down? And there was some issues. I can't go into a lot of details of what the problem was, but failover had failed effectively, and because it's a hospital, they're manned 24 hours a day. So it was actually the ICU that went down and the neonatal intensive care. So the NICU, if you've ever heard of that, that went down. So that was a major issue for us. So I went ahead and I had to jump on the box through the console and bring the box back up. Actually, there's a software bug in the iOS version that I was running. We've since rectified that, and it was running relatively old code. The hospital had the mentality of, if it's not broke, don't fix it. I said, okay, I disagree with that from a CCIE perspective, because if you're running older code, there are chances that newer features are available in newer code, and they weren't running anything really what I consider a corner case. They weren't coming up with some really weird design. They were following best practices. The design looked very similar to what this guy does. It looked very similar to this design. The difference between the two was they didn't have the right iOS image to support the failover. They had failover enabled, but they had never tested it, and they just assumed that it would work. Well, I never assume that a failover is going to work. I make sure I test it out. I'll pull a cable, see exactly how it's going to respond. It's the only way you're going to know. So I had to download an iOS image for them, and I had to upgrade it because this guy was on a couple revs higher than this guy. They didn't keep them in sync. Things went buggy. Problems happened. I got called, and it was just a matter of going in and figuring it out. There was also a minor misconfiguration on this guy here, was set to preempt to him, and he was set to preempt to him, but there's a loop. So that they weren't actually talking to each other correctly because the preemption was incorrectly set. And so they were looping between each other. And that was the problem. And so once we rectified that problem, it was actually a minor software bug. And I went ahead and I was able to identify that because I'd seen it before. And I took care of that problem. But that's one of those things where people ask me, can you pass a Cisco certification when not having any experience in the real world? The answer to that question is absolutely. You can pass any certification as long as it doesn't require you to have any real world experience. However, the certifications don't always teach you everything you need to know about production equipment. So there are things that I know about, iOS codes and bugs and issues that I've seen in production that never are touched or talked about inside of a certification. So it really depends on where you're looking. So that's one of the things where I'd say that experience outweighed the certification, but knowing how to identify the configuration and noticing the errors, the CCIE part of it came into play, and that helped me because I was able to identify very quickly that there was a misconfiguration. And once I changed that, and then I realized that there was I changed the configuration and set it in place, and it still wasn't working. We reloaded, that still didn't fix it. So it was an iOS upgrade, and we fixed the problem with that. And didn't take very long, but you can probably imagine with a hospital with an ICU right after Christmas, that's a big deal. And all of the important people for the hospital were alerted to it, and pretty much were up very, very early that morning. The conference call I was on quickly grew from 3 or 4 people to almost a dozen. So eventually we got to figure it out. It took us a couple hours, but we got to figure it out, and that's the important part. is, can you identify the problem? And that's one of the things about the CCIE that people tend to misinterpret. It's not always about being able to just pass a test, because there are parts of the CCIE lab, whether it's troubleshooting, diagnostics, or configuration, where you have to think critically. You know, okay, there's something wrong. What do I have to do to fix it? And based off of whether a show command or a debug or a trace route or whatever method you use to identify the problem, you have to be able to go in there and identify that. And if you can't do that, then that's going to be a problem you need to figure out. You know, more time spent on that particular area. But that's what I wanted to cover here, because I find that more people that they don't have a fundamental understanding of how this stuff works, it's very difficult for them to identify the problem. So that's pretty much what I wanted to cover in this video. I hope that this has been informative for you, and I would like to thank you for viewing.